what was the negative edge of the clock pulse called in the last class?
Bam.
Bam. Good. Yes, I want you to remember it like that. I don't want you to remember it as positive going edge transition of the clock pulse. That is a straightforward, professional, dry, uninteresting way of remembering it. Unless you make your way of remembering things interesting, you will not remember things. But boom bam is a good way of remembering things. Please remember boom bam, because boom bam will come again and again till you are practicing engineers in silicon fabs. You will meet the problem of boom bam, the issue of boom not coming on time called jitter, right? The problem of distributing the boom and keeping it at a fixed distance from the bam, what is called skew, right? All of these are boom bam issues, right? But if when you hear after 15 years or 20 years or 30 years, right, I may not be in that same room, but if you hear somebody expounding on clock distribution issues, master slave clock distribution, just say he's talking about boom bam. Right? Once you simplify it, nothing seems too daunting or too difficult ever in your life. So I think remember it that way. Boom bam. We had described a single transfer this way. I had just told you about the high Z state in data. I think I should bring up the whiteboard because I think I have forgotten where I have to run. Anyway, let this be on screen. Okay, so I had talked to you about high Z, high impedance state, tri-stated data, and the transition of the data to a valid value. Here there was no data, and here it became some data. So this sausage-like thing here is a place where the data has assumed some value, whether it is 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. This diagram out here, I mean this transition here and this transition here. Now in the second diagram, you'll see that the transitions don't occur at the bam or the boom. Right? They are a little bit above or below. So you'll see that they are linked. But you know this transition, for instance, let me go to that laser mode. This transition, for instance, occurs after this boom. Right? How much after? Depends. But after. This transition occurs after this BAM. So this BAM is sort of linked to this transition like this. I should draw an arrow. We often draw arrows, but in this particular diagram, Professor Sarangi has not drawn an arrow. Right? That's another thing. We in Orissa, we don't say Sarangi. It's only in the Delhi. Delhi has put this bad habit of saying Sarangi. We say Sarangi. Right? So Professor Sarangi. So actually, even Professor Sarangi pronounces his name as Professor Sarangi because he has got northernized. But it is Professor S.R. Smriti Ranjan Sarangi. And so Professor Sarangi's book has this arrow. And we talked about this arrow. I told you about wave drum. So these links are not drawn here, but mentally you can draw those links. Now, there can be multiple transfers. So there can be one transfer here, one transfer here. So this is the same address transition as seen by the master and as seen by the slave. So you can have multiple cycles of transfer. Over what? Over these buses. Right? So whoever it is, I'm sorry, there's an aeroplane going up overhead. Whoever it is who is putting the address on this bus will, after the address, put the data. So that's the thing we are actually talking about here. Now, synchronization is an issue. For instance, if you look at this transition, how does the receiver know that something is valid? Right? For instance, how does the receiver know when to read the data? Right? Number one, the receiver may not have the same clock. Number two, this delay between this point and this point, this point and this point, this BAM point and this point, these delays may change and be variable. They are not always fixed. They depend on the bus. For instance, if I just illustrate what I'm saying, where is my whiteboard? Okay. So if you have, for instance, if you open a Apple Mac, or you open your laptop, on the motherboard, you'll see that there is a CPU, of course. And from the CPU, you'll find lots of copper lines going like this. Well, not exactly like this, but like that. Right? And they'll be in parallel like this. So that's the second copper line. I'm not drawing it very well, but I hope to give you an impression at the end of it that it's a very busy set of lines which go out of the CPU. Because you see, 32 pins, right, all going out from one segment of the chip. Right? That's a very busy set of wires going out. Right? So when you have such a long set of wires, what we call the address bus or the data bus, right, you will obviously remember that, okay, if this is your data bus, this intestine-like thing I drew here, each of these gray lines is a copper wire, of course. Right? So if you look at that, you will be able to simplify this by saying, okay, that's a wire, and on this side there is some load. So on this side there is some load. So let's call this some RL. Of course, each of these things has an RL. Okay. Hopefully the RLs are well behaved. We don't know that, but hopefully they are. But if I draw one of those wires, there is a RL here. Right? And you will be able to take this long segment of gray and change it into, let's say, one resistance, then another resistance, then another resistance. I mean, that distributed resistance of this wire is going to look like this. And so I can lump it, and instead of having a distributed resistance along the wire per running centimeter of the wire, I can say that, well, okay, let me simulate that resistance by so many resistances. That's one thing, the resistance part of it. You will also find that there will be these capacitances which you can draw out here. So any long bus will have these. So that's a badly drawn capacitor.
Sorry, I don't know that.
That's Alexa listening to me. Fine. So
I'm designed to protect your privacy, so I record audio only after your device detects the wake word.
Okay,
or if
Alexa.
The action button is pushed.
Alexa.
On echo.
Shut up. Thank you. This is like having a woman at your elbow all day. Okay, now this is a capacitor set which is throughout the bus distributed. And if you look at this entire thing, this system of R's and C's, of course, each of these systems is like a block RC, 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 right? And I'm sure that if you look from this side or you look from this side, you can Thevenize this and make it one R and one C, right? So that can be R equivalent, right? And C equivalent. Right? But that's not what we want to do. We don't want to get an equivalent of this. We want to know that this bus is full of capacitances like this. Now the story becomes a little more complicated when you have another bus. Right? Let's say I draw the other bus, another wire of this bus like this. I have to then draw this bus just like I drew the previous one with its own resistances. By the way, nobody in IEEE actually draws resistances like this. The accepted way of drawing a resistance is like this. This is how we draw resistances. We don't draw it with that squiggly like this. It's not drawn like that. But anyway, I have drawn it to show it very clearly as a resistance. Now you will have capacitances here which are connected to ground. So a capacitance connected to ground and so on. But you will also have these other capacitances like here. So between these two lines, you will have these capacitances which are called coupling capacitances. So between two copper lines which go like this, right, you will have between the two lines, you will have a parasitic coupling capacitance. Now, the longer the line is, right, the more the number of these capacitances and resistances. Right? So, if you look, as I said, as I started to say, if you look at the motherboard of an Apple or of a laptop, let's say made by Lenovo, or a badly made Taiwanese laptop, you will find that the net effect of this is that you have a huge R and a C. This entire thing looks like a RC filter. So if you have an RC filter, then if I redraw this, if I have a CPU on this side and I have a load on this side, right, and in between I have this huge RC filter. I mean, this RC filter is equivalent of whatever set of capacitances I had drawn in the previous diagram. Then obviously when I put in a textbook waveform on this side, right, the RC filter will pass all the low frequencies and not pass all the high frequencies because the RC filter does that, isn't it? So what I will get out here is something like this. So you can see most of the lower frequencies of that red signal are preserved, but the higher frequencies, the ones in the Fourier series which give rise to these sharp edges, those are gone. Uh, I hope everybody understands this part, that if you put a sharp textbook signal into a low pass filter, only the lower frequencies will survive because it's a low pass, it passes the lower frequencies and the higher ones will go away. So when you reconstitute the signal from its Fourier components, the higher components are all gone. So if the higher components of the signal are gone, what you get on this side is this red signal. So that's the red signal. So this is the red signal which I get. Right? Now, if you look at this signal and you look at this signal, right, and you come back to my, where was I? Here. You come back to this. Signals, therefore, will have a variable amount of delay because those capacitances are not predictable, right? So the rising edge is no longer very sharp. The slewing is not at all perfect. So those delays are not predictable. So how will a receiver then know? I mean, Professor Sadangi actually asks this question in his book, right? Uh, so he offers this second line as an answer, right? So what he's saying is the receiver may sample the clock in the keep out region and it cannot sample the signal in a certain interval around the clock edge, right? That's the setup time actually. What he means really is that if you have a transmitter, right, that's the CPU. I can call it CPU, you can call it transmitter. It emits a signal and you have something, a peripheral or the load, whatever that is. What he's saying is, okay, this is a receiver. As far as the signal is concerned, this is a transmitter. If you have a signal like this, let's say this is the transition period to the clock. Suppose I have a signal like this. then how does this fellow know how to sample the signal? Right? We know that we are supposed to sample the signal here, right? We are supposed to sample it here. We are supposed to sample it here. But how does this fellow know? So that's the question which is being asked. So one of the ways in which we do it is we try to recover the clock. I'll come to that maybe for a slide if I find a slide on that. The receiver actually samples the clock. So effectively, not on a motherboard, because a motherboard fortunately has the boom bang clock available to all chips. Right? On a motherboard, there is a boom bam, which every IC is listening to. We call it the global clock, right? Because that boom bam is going on all over the motherboard, finding out things like this, where to sample, is not a very, very difficult task, right? But it becomes difficult when things are not on one motherboard. About your communication engineering is a phase locked loop which actually creates this clock. So you create a clock which goes like that, and, and on every positive transition of this clock, this one, you generate this sampling signal. The problem is, how do you generate this clock? And the answer is, you generate it using a PLL. Right? How many of you remember a PLL from some other related communication engineering, introduction to communication engineering, signals and systems course? Have you heard the term PLL, phase locked loop? Or does this sound? I mean, I'm diverting, of course, but does it sound um, like a incoming signal, local signal, um, band pass filter, and then a VCO, the VCO frequency coming in through a divider, divide by n, and coming out here. Do you recall this diagram from any of your courses? If you don't, it's fine. It doesn't matter, because this particular thing is called a PLL. Right? And what it does is it takes an unknown signal out here and it locks it with a known signal out here till the known signal is in phase with the unknown signal. So the known signal and the unknown signal ultimately go into a phase lock. Right? Now this is the incoming signal. This one. Right? You don't know anything about when it is rising, when it is falling, but you have total control over the local signal. So what you do is you adjust the beginning, the starting and the ending of the local signal till it becomes aligned with the incoming signal. So this alignment is what the phase locking is all about. Right? So this particular module locks the receiver's clock into the incoming signal's clock. It's not a very difficult block, and fortunately manufacturers actually make this available to us as a 560 or a 565 IC. Right? So you can buy a dual PLL or a single PLL, very simple, and use it to recover a clock. It gives you a beautiful clock back. It's used all the time, right? Especially in telecom. But what Professor Sarangi is saying is that this receiver may sample the clock, not around the clock edge where it is a little uncertain, but in the middle, and then you get the data back. Now, if you have synchronous buses, synchronous, you remember the Greek word chronos, sync is the same time, synchronous. So sender and receiver have the same clock, right? the signal arrives at the receiver, and then you put this little BAM out here. So I will have to put some pen or something. I think. Okay, maybe highlight. So if you look at this signal, if you generate this signal from the PLL, the one which I just circled in yellow, this highlighter is very nice. I never used a highlighter before. Okay, so this highlighted yellow signal is generated from the PLL. So you should mentally think about a, oh, that's very nice. You should mentally think that there is a PLL somewhere which is producing this signal. And if the input, whatever I drew as the incoming signal is out here, and you look at this as the local signal generated from the PLL, then the point at which you sample, which is this point, this edge, as a matter of fact, I think it is a positive edge, correct. It's the positive edge triggered D flip-flop. So on the positive edge of this green signal, whatever is in D will get latched into the Q of the D flip-flop. That's how a D flip-flop works. Its D becomes its Q on the positive edge of the clock. I mean, that's why it's called a data flip-flop, isn't it? Whatever you put on the D becomes Q. So synchronous buses use a sampling circuit like this. I mean, that's the name for it, but I don't know whether I should write it here. I should write it maybe. Sampling. Handwriting is usually good, but it looks very bad here. Sampling circuit. Sometimes they call it a sample and hold circuit, right? Because once you hit the bottom of the flip flop with that clock pulse, the D flip flop records what was there in D. So it samples at the positive edge and it holds forever till the next positive edge, right? So it's called a sample and hold. I hope you will be mentally filling out S for sample, H for hold. I'm not writing it there, right? But Professor Sharangi puts this diagram in his book, so you can all see that book. And of course, if you have Logisim, you can simulate this and see what happens. There it comes. Last time I said mesochronous, plesiochronous, isochronous, synchronous. Isochronous and synchronous are the same thing. But look at this nice looking complicated name, mesochronous. Right? Mesochronous is okay before the boom thing is ready out here, right? You don't want this thing to arrive here. So what you do is you then delay it using this element, right? Uh, so you can actually buy chips which delay a certain signal by 1 nanosecond, 2 nanoseconds, 7 nanoseconds. You can buy these chips. These are tunable delay elements, but they introduce a fixed delay. It means um, basically means don't invite your guest into your house before you cook the dinner for him. So you keep the guest in your garden, right, by putting a delay out here. So that's the delay element. So once you put the guest, delay the guest, the moment the dinner is ready, right, that's the dinner. And when the dinner is ready and you hit it at the clock, the guest should be at the D input. So that's another technique which we use. And of course, there is the possibility of you send the clock along with the signal. Right? That is, don't think that I'm only sending the signal. The receiver must uh, generate a local clock. You send the clock and signal together. After all, on a motherboard, any target and any source and destination chip is only separated from them are separated from each other by some centimeters, maybe 6 inches, about 15, 20 centimeters maximum, right? So send the clock. It means that a lot of clock signals actually snake around the board. Right? But it's a very simple way of making sure everybody hears the same boom. The only catch there is that, of course, that if you have, oh, I erased everything. All right, that's fine. So the only catch there is if you have a motherboard, let's say this is a motherboard, and this is a CPU. My pen color didn't change. This is a CPU, and let's say there are two destinations. Let's say this is one destination, and this is the other destination. I'll draw it in green. Then the clock which is going up to this and the clock which is going up to this are going to arrive at this point and at this point after slightly different times, because one is taking a longer route, longer copper wire, the other is taking a shorter copper wire. Maybe I should have drawn it, uh, drawn it a little closer like this. Maybe I should have drawn it like this. Right? So you can clearly see that one is a very short route, one is a long green route. Now, if you have clocks arriving at different times, right, then obviously you need to put something like this and something like this to estimate the delay and to tune the element. You can see this arrow. You can see, do you see this arrow between these two elements? So you first estimate how much delay is there, right? Let's say it's like saying that the Prime Minister is going to inaugurate at one go 20, 20 dams around the country, or 20 foundation stones he's going to lay around the country, or maybe in different countries. Now, the question is that it has to be at the same time. But when he cuts the ribbon in Delhi, right, you are going to have different delays with which it is transmitted to different countries. So you have to adjust those delays, saying, okay, he must have cut it 5 minutes before in Delhi. That's the known delay. I tune my delay so that my program starts at 9:05 here in this country, so that I also cut it at the same time. So basically, it's a tuning of that delay. So that's called a tunable delay element. And you have asynchronous process where clocks are not necessary or not transmitted. So here Professor Sarangi actually says exactly the same thing which I have been saying. That's a PLL. He calls it a clock recovery circuit, but it's usually implemented using a PLL. By the way, when I said, have you met this PLL? I didn't hear any yes, no, nothing. So have you not met the PLL?
Not met, sir.
Not met at all. So it's a very interesting chip. I would suggest you look at this. If you have a web browser open, look at this IC. That's a very commonly available PLL IC. But of course, that PLL IC is only for very low signals. Right? But it's a very commonly used PLL. You can use this PLL. I don't remember actually 564 or 565. It's been quite some time since I actually looked at this card. But I'm sure that you can all find this out very any yes, okay, and 564 okay, yeah, even this one 560 and 565. 565 has two PLLs in it, and 560 has one PLL in it. Right? Very interesting chip. I think you definitely merits a look. And can I just see whether it gives? Been quite some time since I drew this PLL circuit. So maybe if I just verify what I was talking about. Yes, okay. So phase detector, low pass filter, VCO, and a feedback path. Of course, I had drawn a divide by n here. That's called a multiplier of PLL. But you can understand it if you read this. That is, it looks daunting, but again, nothing in electrical engineering is actually daunting. So please look at it. I am not going to go into this, but my diagram was more or less correct, except my diagram was a little bit more than this. It had a divide by n counter out here, so that's fine. That's there. So we have this point. I seem to have taken a lot of PowerPoints from Professor Solangi's book. All right. Then, instead of a clock, the fellow sending the data sends a strobe along with it. So these are all methods of synchronizing buses and I/O transfers. I know we are talking about this in context because whenever you do I/O, right, you are always talking about something like this. Right? There is always that you are doing an I/O from a CPU to a peripheral. So there is always going to be this particular in-between thing between the CPU and the peripheral. So the bus, which is the in-between thing, will suffer from all these problems which we are currently describing. So that's the context in which we are actually looking at this. Um, you can also have handshakes. Right? So that's Professor Sarangi's book, which says if you have a data, you send a strobe along with the data. The strobe rises a little bit after the data becomes valid. So the data becomes valid at this point, and if you go down at this point, a little bit after this point, the strobe is raised. Once the strobe is raised from low to high, that's the point at which you say that, okay, I have reliably read the strobe and now I know that the data is valid, I'll do something about it, and you acknowledge the strobe. So the strobe, which is raised by the sender after the data is valid, is acknowledged by the receiver to the sender. And at this point, the receiver has this much amount of time, almost this much, right, in which he or she, I mean, senders, receivers don't have a gender, right, but the receiver can actually sample the data in this much amount of time. Because if you go to anything like this, the data out here is now going to change back to something, so you don't have much time. So only in this part you can sample the data, and after you send back the acknowledgement, the receipt of the acknowledgement which you send will tell the fellow who is raising the strobe that he can now bring the strobe down safely because the sender has got the strobe. And it also tells the data sender that you can change your data now. I have actually started sampling it. So these are two links out here. Fine. So I have redrawn this using WaveDrum because I found WaveDrum so much fun that I thought I should redraw one of these to just see what WaveDrum does. So that was how I chose to put the links, and I actually added to this arrow what this arrow does. So data asserted, assert strobe. I think I'll have to go to the mode like this to see this. Okay, so data. So once you have address, an address comes a little bit after the boom. So there's a boom going on here. There's a bam going on here. So boom, and after the boom, the address changes, the data address, okay? And there's a small inconsistency here. I've written data here and I've written address here. I think I should have written address here. Right? So that inconsistency is because I got carried away by my excitement at discovering WaveDrum. But anyway, so once you have this point, this transition A, this means that data has been asserted and you assert the strobe. So that leads to the strobe going high. So then when the strobe goes high, right, the acknowledgement for the strobe, the acknowledgement, so this is the strobe acknowledgement. So this acknowledgement goes high. Once the acknowledgement goes high, the data can change and the strobe can go low. Right? I think I've made a mistake here, but you get the idea. Right? Um, I think I drew the same diagram which I have drawn out here in a bigger one. I'm very prescient. Okay, all right. So that's very nice. So we call this a handshake mode. So you can have a four-phase handshake, right? And that repeats over and over again. You can also have a two-phase handshake. So we, instead of asserting and deasserting, we toggle their values. No need to pause. The sender will start sending the next bit after it says the act line is toggled. It doesn't wait for the end of the act line. It starts the next transmission just after the act line. So the advantage of that is that anyway, after you put the data, you have to raise the strobe. So even if you start sending the second, uh, what shall I call it, installment of data, second EMI of data, it doesn't matter because until you raise the strobe, I'm not going to do anything. Right? So if you send this data and you don't send the strobe, then I'm not going to sample this. Right? So you can do whatever you like, but until you send the strobe, which is here, I'm not going to do anything with the data. So I will actually, in this, miss this data because you are not sending any strobe with this data. So that's up to you. So that two-phase handshake will suffer from this, that this particular middle data set will not be sampled. This input operation and output operation is summarized in Professor Solanki's book like this. No, in Hamesher's book like this. Uh, a little difficult to understand because Professor Hamesher does not put any information on these timings which one needs when one is reading this timing diagram. But what it really means is this positive boom of the master ready is linked to the positive boom of the slave ready and to the data transition. Now you have to read it like that. So the positive edge of this signal is linked to the positive edge of this signal. So these things happen. Right? On an asynchronous bus where there is no clock, this is needed. On a synchronous bus where everything happens on a boom bam, it is optional. If you have it, it's good. And remember one thing, a handshake or a data transfer is like the gamcha. When you raise a strobe or you raise an acknowledgement in response to a strobe signal, you are raising a gamcha. Right? Tying a gamcha to a pole, if you remember our gamcha analogy. And so that's what you are actually doing. Now there is this issue that what happens if there is only one bus? Where is that bus? The bus is here. Okay, so I need to see where the bus is. Okay. Highlighter. This is the bus. Okay? And to this bus, there are two masters which need access. That's the first master, and that's the second master. Now, when you have two masters, what do you mean by a master? A master is somebody who owns the bus for some amount of time. So it doesn't have to be a CPU. It can be anybody who takes control of the bus for a certain amount of time. Like, for instance, suppose you have a town in which civilized people live. We go to school, we go to college, we go to the market using the road. But then we as citizens are masters of that road because we pay taxes. But occasionally you find that somebody comes and says, no, today there will be a band, there will be a gherav, and today I will lock all the roads up and nobody can come on the roads, only my people will march on the roads saying we want, etc. So at that point, what happens is your control, you the citizen, lose control over this bus, and the person organizing the gherav or band gains control over the bus. So this bus starts belonging to the fellow who is doing the gherav, right? Not to the fellow who paid the taxes. So if you have two masters, right, in between the two masters, you need a arbitration circuit. So that's an arbitration circuit which says, okay, I'll give you the bus for certain amount of time. Like, for instance, if you want to organize a gherav or band in a civilized country, you apply to the police. You write an application saying, dear police commissioner, I am understandably annoyed at this particular part of the society, and I would like to take control of the roads of your city for one day, and that day is a working day, obviously. Right? On some working day, I would like to do that, and the arbiter, who happens to be the police commissioner, then tells the other master that okay, this Gherao fellow is going to take control on Friday, so you can go for a long weekend on Friday, Saturday, Sunday. So that arbitration is granting of the bus so that the second master can take over the bus. And at the end of Friday, he will actually call it a day, congratulate himself on TV or herself on TV, and hand the roads back to you so that you can go to office on Saturday. So this handing over is also called granting. So it's a bus granting. And both of you actually talk to an arbiter or an arbitration circuit, which does this granting of the bus. Is this too difficult to understand? That if you have a bus and you have multiple ICs which need to address or put data on the bus, arbitration is one way of reliably making sure that the bus belongs to only one person at the same time, at one time. Is that coming through in all this storytelling?
Sir, like, uh, who controls that? Who owns the bus at the time? Like, what on what basis buses are allotted?
On what basis buses are allotted? Okay. Number one is master one may schedule a granting of the bus to master two. We will meet that when we look at direct memory access or DMA. Right? That's one way. Master one actually wants to give the bus to master two to use. Right? That's one way. The other way is the master two says that I am a master two and I need the bus, and it's the arbiter's decision to say, okay, after 50 clock cycles, I will tell master one to withdraw from the bus. Withdrawing electrically means putting a high Z or a high tri-state condition on your bus. So in a storytelling mode, what it means is that you lock yourself into the house. Lock yourself means you do not make yourself available outside the house. You stay inside your house. So the CPU can actually lock its doors, right? So this master one can lock its doors by putting a high impedance state on its bus from inside. Then it looks as if it is not visible any longer. Right? So that's the physical way in which the locking out happens. But if you are asking how and why should master one relinquish the hold on the bus? Well, we hope that whoever designed this particular circuit intended that master one and master two do two different useful things, or whatever they do together is together taken together more useful than either one of them. For instance, you might have a master one which does some computations. You may have a master two which controls the network. So if you have, let's say, a video movie coming in over the network, master two, which is handling the network, may tell the arbiter that I am actually streaming a video on the network and I would like to actually display this on the device for the next 75 clock cycles. So would you please ask master one to shut up? Like I asked Alexa to shut up. So master two then tells the arbiter that can the master one please shut up for the next 75 cycles so that I can transfer something to the buffer of the display and the movie will keep playing steadily. So master 2 has a legitimate excuse to take possession of the bus. So the arbiter will tell master 1, okay, please back off for the next 75 cycles while I give the bus to master 2. So master 2 after 75 cycles gets the bus, transfers let's say 1 megabyte of data, right? That's a buffer full of data, and then says, okay, I'm done. I'm relinquishing the bus. I'm leaving the bus. I'm giving the bus back. Right? So then the arbiter takes the bus back and tells master one, okay, you can take the bus again. He's finished. Is that answering your question?
Yes, sir. And sir, what are those BR1, BR2 signals?
So bus request 1, bus request 2, bus grant 1, bus grant 2.
Yes.
Then so you request for a bus. So these are two deliberately put ICs. They are not malicious like in a Ghera or Band. They are deliberately put. So you request the bus and you are granted the bus. So you will see that the linkage is that if you request the bus, you will be granted the bus and they are linked. You will be granted the bus after you request the bus. Right? Similarly, if there is a bus request 2, which is coming from the second master, then it gets a bus grant 2. Right? Once the bus grant 2 is relinquished, the bus grant 2 is relinquished, then the bus grant 2, bus grant 1 can happen. But till you keep your bus grant 2 high, the bus grant 1 cannot be raised high. So you can see that there is a timing and synchronization issue which the arbiter has. Right? Of course, you can of course see in this diagram that uh, these are the two signals which we are talking about: BR1, BG1, BR2, BG2, and their interrelationships are captured in this diagram. Right? Is that okay?
Yes, sir.
Fine. So let's go forward. So there are two methods for this arbitration. Right? One is you have a central arbiter. You can also have a daisy chained arbiter. Right? We'll just look at that. For instance, in this particular slide, what it says is, if you look at this, this is master 1 and master 2. In the second slide, these are called multiple transmitters are connected to a single bus. After all, master 1 and master 2 are transmitters. So this is transmitter 2, this is transmitter 1. Right? So when you say multiple transmitters, we actually mean they are generators of signals. So that's what. Okay, I should erase ink on this slide. I should erase the ink on this slide. Fine. How do they get access? So two methods. One is a centralized arbiter. Arbeit, the word Arbeit means to work. Right? In German, the word Arbeit is work. As a matter of fact, their MTech diploma is called Diplomarbeit, which is the diploma work. So Arbeit is arbitration's progenitor, centralized and daisy chain. So this is from Professor Sarangi's book, but I think I copied it without the McGraw-Hill. So I think I have put this from Dr. Sarangi's book. So centralized arbiter is very much like the previous arbiter you saw, this arbiter, which is in Hammersher's book. This is from Hammersher's book. This is from Professor Sarangi's book. You see, I have a lot of help, right? Which is why I don't have to give you my slides. They are all in the book. If I distribute these slides as my slides, that's not going to be correct because they're all their slides, okay? All from Hammersher's book and from Sarangi's book. So this arbiter is a central arbiter. Each device which wants the bus to be handed over to them is going to make a request to the arbiter. Now, this the first part. This one, you understand already. It's just a question of and arbiter thing. But the second one is a little bit more interesting. It's called daisy chain arbitration. Do you know what is a daisy chain? Do you know what is a daisy chain?
No, sir.
Oh, why a daisy chain is a daisy chain?
No, sir.
Okay, so a daisy chain, I don't know, it seems like a gender specific thing to say because boys can do it as well as girls. But when girls play, and one of the plays of girls, common plays, um, I say it because I have a lot of sisters, is to pick flowers and poke one end of the flower into the front of another flower. So you can actually actually take a flower like this, right, and poke it into another flower like this, right, and poke it into another flower like this, and it actually locks together and forms a sort of mala. Right? So the daisy flower is particularly amenable to this. You can do it with other flowers too. But daisy chaining is a way in which the daisy flower stem of the daisy flower is pushed into the other flower. And that stalk is pushed into the next flower. That stalk is pushed into the next flower. Which have you ever done that in your childhood? I mean, has WhatsApp and Facebook ever given you time enough to do this? I don't know. Yes or no?
Yes,
Anybody who has gone out into a lawn or a garden and picked flowers as a child and done this?
yes, sir.
Oh, you see, now it wasn't gender specific. I got a yes from a boy, so it's fine. So, well, as children, we used to do this, so it was particularly simple for us to understand. I don't know if this has a um, of a daisy chain. Ah, yes. Oh, yes, 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 yes. All right, very nice. So you can see that what I was talking about is this. Right? So that's a daisy chain, and somebody has made a bracelet out of a daisy chain. So that's a daisy, right? And this little girl has a necklace made out of daisies. So that's a daisy pushed into another daisy. That's very nice.
Daisy Daisy by Sea Girls from Spotify.
Alexa, stop. Very, 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 very intrusive device. Okay, so now let's go out and go back to the daisy chain. So my point about the daisy chain was whenever you have peripherals, one the output of one fitting into the input of the other, you actually have a daisy chain. Right? Now look at this particular structure. Um, do I have a story for this? That you have an arbiter here, right? That's the arbiter. Oh, this is very interesting. One possessing the bus. Then device 2, having used the bus, then passes on the token to device 1 passes on to device 2, passes on to device 3, passes it on to device N, and whoever doesn't need the bus passes it back to the arbiter. Right? So the arbiter injects a token, and the token passes from device to device. And the last device, it's the last device who needs the bus or the last device in the chain of devices sets the release signal and destroys the token. Doesn't return it, destroys it. Once the token is destroyed, nobody else can grant the bus, so the arbiter has to generate another token. And so this method of having single token based control or multiple token based control is very familiar to computer scientists who uh, need synchronization in distributed networks, and they actually have tokens which are modeled using Petri nets. So you will find that when if some of you are from the computer science background, when you go into the fourth year or end of third year, you will use a tool called the Petri net, which extensively uses tokens to actually uh, depict or describe this sort of token injection and token possession as a method of synchronization between distributed devices. I am not talking about Petri nets because I am not talking about that course now, but you can easily see that if you have only one active token, you will always have only one device capable of possessing the bus. It's as if whoever has the token gets to access the bus, right? Now that That is a good way. It's like saying I have 1,000 devotees wanting to pay their respects to Lord Tirupati, and I generate one token, and I say whoever has the token can go and visit the Lord for 5 minutes or 10 minutes. Right? So it's a time token. So you go, you have the token, you go, you put your prasad, get your prasad, come back, give the token to somebody else who goes. You see, it's a very, very synchronous way of giving the token and granting the bus. This sort of daisy chaining we will again meet. This daisy chaining will come about in the SPI bus, the serial peripheral bus, right? So you will find this is not as oddball as it sounds in this slide, but it'll come later. Any questions so far?
Sir, like in this daisy chain method, if like last device wants request for control over the bus, it has to wait till the token passes from all the devices, even though they don't need.
That's right. It is unfortunately the way it is drawn, it does mean that the token will pass from device 1 to device 2 to device 3 up to device n. But but you can see one thing, that the token will pass from device 1 to device 2 not through some private bus. That blue arrow looks like a private bus, but there is no such private bus. It will actually pass over the bus. Fine. So there has to be a bus transaction over which a token will pass from device 1 to device 2. So there is nothing which says that a device 1 cannot pass it to device n. So if you design your protocol correct, if device 2 says, no, 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 I am not going to go to Lord Tirupati today, there's nothing preventing you from giving it to the next fellow in line and not giving it to device 2. So you can see that this is possible. Right? As an answer to your question, this is possible, but you have to design it. Right? Normally, we would go with the most conventional and staid way of designing it in sequence. But all of these green transitions which I have drawn are very, very possible, and it can be done. Is that answering your question?
Yes, sir.
Yeah. Okay, maybe I was thinking of an example which I could have said, but I think for this course, I don't have to use that example. For instance, suppose I have a central central connector like this, and I have um, devices hanging from the central control. I'm going to erase all this. So I'm doing a dirty drawing on top of my slide. Suppose I have um, 1, 2, 3, 4, 5. So if you look at it visually, it seems as if 1 is a neighbor of 2 and 5. But if you look at it behaviorally, you can see that one can actually talk to 2. That's possible. One can also talk to 4. So 1 and 4 are neighbors, just as 1 and 2 are neighbors. So it is only that physically they look as if they are neighbors because they are side to side like this. But logically, 1 and 4 are equally close to each other as 1 and 2. So if you look at this behavioral and physical way of connecting devices, they are two different things. So what looks as if it is not a neighbor is behaviorally actually a neighbor. Right? It's like 5 friends or 20 friends sitting around a round coffee table and drinking coffee. You see, any friend can pass a biscuit to any friend. It's not necessary to the friends to both sides of he or she, or himself or herself, isn't it? So you can imagine the central hub and spoke configuration like that. Right? There are very interesting problems which come up not in the electrical engineering domain, but in the computer science domain, which are very interesting to look at, like the dining philosopher's problem, which are basically token arbitration problems. Right? So if you ever find the time, please look at such problems. Okay, let me go. So this story is uh, well captured by how panel discussions are arbitrated. Have you ever seen a panel discussion in, let's say, a youth festival or in a some seminar in Bhubaneswar? So there are these four invited speakers, and the director, Professor Rajakumar, is the arbiter, and he says, "I will invite speaker one to come and say something on this question." So then speaker one says, "Thank you." That's the handshake. "Thank you, Professor Rajakumar." Implicitly, Professor Rajakumar. And he rises and comes to the podium and addresses you for about 10 minutes or 5 minutes. So what does he get? What does he possess when Professor Rajakumar gives him the opportunity to address you? He possesses the medium of that auditorium. Between the podium and the set of students or faculty listening to his talk, it is it is four speakers who have been invited from outside, who are being arbited by Professor Rajakumar to and granted possession of the medium in the auditorium. So once speaker two goes back, and that he goes back by saying, "Thank you for your attention." That's a handshake to Professor Rajakumar, who can now say, "Okay, I will now invite Professor so and so, speaker number two, to come and address us." So that's how a panel is arbitrated. There is a central Professor Rajakumar, who is doing this arbitration, and there are these speakers who come in sequence to the podium and address and go back with a handshake, implicit or explicit, to the arbiter. So panel discussions are like central arbitration. But what about group discussions? You must have seen group discussions. You must have heard about group discussions. All these people who go in for job interviews, MBA interviews, they come back and tell us these stories about, okay, there was this one-way window through which the committee was looking at us and listening to us, and we were seven of us sitting around in a circle, and they were looking at who was most aggressive, who used to take the conversation thread and talk, who was reticent, who used to be shy, who used to go into the background, and we got marks. I stood on the table and kicked two participants off their chairs, so I got selected into XLRI Bhubaneswar. Haven't you heard these stories about group discussions? So when 12 people sit around a table and a group discussion is monitored, basically when you start a conversation, how do you start a conversation? You grab a token, the token of the right to speak. That's the token you grab in a group discussion. Right? How do you grab it? You grab it by two methods. One is by assertion. You say, "I want to grab it." The other is by interruption. You shout louder than the other fellow. So the token ultimately passes to you. But if two of you wish to grab a token because it's there for grabbing, and two of you speak, right? And then it's hodgepodge, because if two, three, four of you speak together, nobody listens to anything. So in a group discussion, you have that possibility that unless you enforce a rule, only one fellow can speak. However he speaks, only one fellow can speak. Whether it is by uh, who goes first, that's one way of arbiting the group discussion, or giving the speakers a number, 1, 2, 3, 4. So if I am 1 and you are 4, I always have priority. So if I start speaking, you have to keep silent. So that's a policy. It may be an unfair policy, right? It may be an unfair policy because the lower numbered fellows will always get higher priority. So it is unfair, but that's a policy. So you can always do a similarity check between group discussions and token-based access to buses. Not exactly, but approximately the same thing. So that's the story time for the two arbiters we have talked about. Now, there is another aspect to this. Why I even talk about this aspect is Professor Sadangi's book talks about this very briefly. Right? It says if you have one bus, if you have one bus and you have the following properties about that bus, right? So just look at this. A transaction ties up the bus. That is for sure. When something is talking to something, the bus is not available to anybody else. Right? And a transaction may have long pauses in the middle. So you have, suppose you are a speaker who has been invited to talk, right? And you are given to long pauses. Right? They may be meaningful to you, but they may not be meaningful to the rest of the world. Right? We had a prime minister who used to pause for long periods, right, during his speeches, and it was very worrying. Has he forgotten what he's going to say next, or is he just thinking of what he's going to say next, or does he expect me to think? So these long pauses, when the bus belongs to somebody but is not being used, can be used. You can, when you have a pause, you can, for instance, you are addressing the parliament and you are planning a 5-minute pause between sentence one and sentence two. You can give a notice to everybody saying 5-minute pause coming up. Go quickly get a samosa from the cafeteria. Right? I mean, that's what YouTube does to you, doesn't it? Ad coming up in 4 seconds. Right? What does that mean? Quickly leave the YouTube channel and go to the bathroom. Take a bio break. So you can always use this transactional pauses. So you can have a split transaction. So you have a request sub transaction and a response sub transaction. So during that pause, you can actually do a second task. That's flexible. It is simple. Right? So that's one thing. The other way of looking at this is, can we have multiple buses? Yeah, you can have multiple buses in the same motherboard. In the motherboard which you are looking at in this course, 8085, 8086, that's not very common. We usually have a single address bus and a single data bus because it's easier to handle, right? But if you have a really competent CPU, right, something like your i5 or i7, right, those CPUs are very fast CPUs. The clock cycle, the master clock on the CPU board is like 3 gigahertz, 3 gigahertz, 3.2 gigahertz. 3.2 gigahertz is a lot of things the CPU can do actually. So what you do is you split the bus. You say that okay, there is a bus on the north side of the CPU, there is a bus on the south side of the CPU, and these buses are separate. There are the set of devices on the south bus is different. The set of devices on the north bus is different. And those north bus can be given to somebody to use, and the south side can be given to somebody to use independently. Am I with you? Are you, or rather, are you with me so far? Just imagine it this way. You know the main building of IIT Bhubaneswar, that that entrance from which Professor Rajakumar enters and goes up to his office. Are all of you have seen that entrance?
Yes, sir.
Good. And what is in front of you? There is a staircase which leads to a corridor on top. You turn right and you go to the end and you land up in the director's office, isn't it? That's how that building is organized. Yes.
Yes, sir.
Good. So that staircase and that corridor are like a bus. Now you also know that when lunches etc. are organized, just when you go up to the first floor and turn right, you go to Professor Rajakumar's office. But when lunches are organized by Professor Rajakumar, you have to turn left from the staircase, go a little distance, and there is a big hall. I think it's called the Senate Hall, maybe. There's a big hall in which is big enough for a lunch. Now, suppose there is an event in which Professor Rajakumar is coming with the Prime Minister and the President, and the cafeteria fellow is coming with 2 sacks of samosas and 3 buckets of tea. Now, naturally, there is only one corridor. He has to enter through the same entrance as Professor Rajakumar. Now, if this samosa man says, I am arriving, my truck will be parked in front of this entrance till I unload my 3 sacks of samosas and 4 buckets of tea, right? Professor Rajakumar has to wait because the bus has been granted to the samosa fellow. Now, the busier the cafeteria gets, the more Professor Rajakumar has to wait. So, if Professor Rajakumar cannot wait that long, for instance, I have something very important to do, and the Prime Minister is saying that he can't wait for the necessary 10 minutes, what your registrar might say is that, okay, these service related cafeteria fellows, can we have a service lift from the back of the building and a service entrance from the back of the building, so that when they bring their samosas, they will go round the building and enter from the back, use a different corridor, and reach the same place. They will never step into your toes. I mean, that's like a south bus. So you have a north bus and a south bus, and Professor Rajakumar uses the north bus, and the cafeteria fellow uses the south bus. And as they say in Shakespeare, never the twain shall meet. The two shall never meet. The cafeteria fellow will only use the south bus. Professor Rajakumar will only use the north bus. If they want, they can use both buses, right? That is, on one surprising day, the cafeteria fellow may go from his bus, climb into the corridor in Professor Rajakumar's office, go down the stairs, sit in Professor Rajakumar's car, and go back to Khorda. I mean, that can happen, right? But it's going to be every once in a blue moon. Or Professor Rajakumar, maybe if he has been out by students, can choose to go back through the service entrance, sit in the cafeteria fellow's truck, and go back home to escape from the students. That also can happen once in a blue moon, right? So a north bus device can use the south bus. So the diagram I am drawing actually is that there is a CPU, right? And it has a north bus, that's north, and it has a south bus, that's south, right? There are a set of devices connected to the south bus. There are a set of devices connected to the north bus. Let's draw them as red because they are important devices. Prime Minister, President, Professor Rajakumar, right? And you will then think that, okay, there will be an arbiter, a security guard for the north bus, and there will be an arbiter for the south bus. So we actually call this, Intel calls this a north bridge controller, and this as a south bridge controller, right? Which is fairly okay because you know that this is the CPU in between. Now, what I'm saying is, it is not inconceivable that a data byte coming from one of the north bus devices, Professor Rajakumar, goes through northbound controller through the CPU to the southbound bus and goes out using the cafeteria's method of. That's possible. Unlikely, but possible. Similarly, a southbound device can actually ask the CPU to store in a temporary register and then go to Professor Rajakumar's office. That also is possible, right? But those transactions are relatively rare. So what we think is, I went to the previous one. So what we think is that mostly highlighter, mostly the transactions of the northbound bus will stay this way, and the transactions of the southbound bus will stay here. So that's a localization of the transactions, right? So it's a spatial localization. You must have read in memories about spatial localization and temporal localization. So this is a spatial organization of the functions. Northbound functions stay in northbound, southbound functions stay southbound. But if you ever meet these names called North Bridge, South Bridge, you know that you're talking about a bridge IC which controls all the southbound transactions, and the north bridge is controlling all the northbound side. So these are multiple bus controllers. Let me erase also. So very clean. Fine. And you will find many more, some more data out here, right? Which is this I have already told you in the last class that you can draw these timing diagrams. I have recommended wavedrom.com to you, but I am recommending Obsidian, Obsidian. You might want to write that down. The Obsidian Markdown editor, which includes Wavedrom inside it, right? And these four other softwares for all diagrams you will need. At least those of you who are in electrical will need this all the time in your life. So you might as well practice. Give it 15 minutes today, right? And it's a pretty enjoyable way of spending your time. Like after a long time, yesterday was a holiday, Deepavali. I spent most of yesterday relearning Tixi timing, right? So Tixi timing is a very interesting curve, which I had forgotten. And because thanks to you, I thought I should look at that 900-page manual once again. Nobody ever reads 900-page manuals. Let me tell you from the heart that I have been at it for nearly 3 decades now. Nobody reads those 900 pages manual. You go in just like you go into a storeroom and pick out a biscuit jar and eat a biscuit and come out. You don't need to find out what else is there in the storeroom. So you enter 900-page manuals with the same principle in mind. Go in there for a specific purpose. I am going to draw a clock. How does one draw a clock? Search for the word clock. Read the paragraph before it, read the paragraph after it. If you ever need to go in and do something else later on, go in again. So don't get daunted. When will I read 900-page manuals? They are not even giving me time between test 1 and test 2 in IITs. You will never get that time. It's been nearly 36 years now since I did my BTech, and I don't find the time. I find time on Deepavali to read manuals. So please have a reality check like that. Are you able to take a photograph of this slide? Because I can't put this on the chat, so I would really like it if at least for the right side of the slide, each of you took a photograph and sort of investigated this in your leisure time. You know, most of you might not, but some of you will, and that's worth it. Okay. Now, to summarize, a I/O interface has a data storage, has a status, has a control, decodes the address to determine a chip select, generates the necessary timing signal, performs any format conversion, right, to transfer data between a processor and a I/O device. So that's probably the reason why I kept this. So to transfer any data between the processor and the I/O device, such as parallel to serial, serial to parallel, parallel to something else. Right? So that is another part of the I/O interface. So to pull together all the I/O related things which we have done so far, uh, this is about it for the I/O side. I don't, whatever else I show here, right? You can easily understand this. Keyboard inputs, display inputs, done, right? We use the word uh, deja vu. Have you heard this phrase before, deja vu?
Yes.
What does that mean?
Already seen.
Already seen. That's right. Your generation has a nice set of acronyms for various situations in life. LOL, ROFL, FOMO, right? Um, Wonderful acronyms. I mean, I wish we had these acronyms later on. There is another very interesting acronym called TLDR. Have you heard of TLDR?
Yes.
TLDR. What does it mean?
Too long didn't read.
Too long didn't.
Long did not read. Too long did not read. TLDR. That's a very nice acronym. Half of the things in my life are too long. I don't read them. Okay. So,
I know one funny one. TGIF. Thank
hmm?
God it's Friday.
Yes,
TGIF.
TGIF, of course. There's a famous hotel called TGIF.
Yes.
That's right. Very, very well used in Delhi. TGIF. Thank God it's Friday. So, you have another IC which Professor Dogra will introduce you to called the 8255, which does this for you. I mean, it actually gives you parallel ports, gives you handshaking signals. It allows you to say that 8 bits are for input, or these 8 bits are for output, or for input and output. It's a very, very versatile chip, and it gives you ports, right? So you can use this 8255, and this is the data sheet for the 8255, to actually create ports. You will find that when you open the 8255 chip, you can create A ports, B ports, C ports, and C ports are individually controllable. So you can actually control each wire of the C port. So you can use it for handshaking. And if you have ever wondered, right? Um, I don't know why I wrote this comment at the bottom. Uh, why I feel like a dinosaur? Well, that's age for you. I don't remember why I feel like a dinosaur, but I am a dinosaur because probably 36 years back I met these chips and now I'm re-meeting them again. So that maybe that is why I feel like a dinosaur, right? So Subratosaurus rex. So there are two chips on this slide, 8250, which actually implements a serial connector. And what I am talking about in this 8255 is something like this, that if you have a CPU which needs to, let's say, implement a, I think I want to erase this, and which needs to implement a 8-bit input and a 4-bit 4-bit input and 8-bit output, and a read write pin. The 8255 actually allows you to do this. So you can put an 8255 here, right? And the 8255 obviously, like any other IO device, will have a data status control register inside. So you can program the 8255 and say, okay, give me one port which is output and 8-bit long, and give me another port which is 4 bits and input. Right? That is by programming the control register of the 8255. And you can say that give me another wire which is for read or write, which I can put 1 or 0. And once you've programmed it, the 8255 will give you these ports. So you can now write to that port, you can read from that port, you can raise that read write pin high. So if you have ever wondered how will I bring these pins out if the 8085 itself does not have these pins, the answer is use an 8255 and get those pins for yourself. Now, the second chip is, I think I have a slide on this. Yes. Oh, why was I wasting my time? Fine. So if you have an 8255 like this, I have fortunately put my color. So data is always blue, uh, status is always red. Okay, control is, I think, yellow, and status is green, if that was the color convention we used. And 8255 actually gives you a port A register, group A, right, and a group B register, and a this should be a group C somewhere. Yes, okay, sorry, I think I got too carried away by, so port A, port C upper, port C lower, and port B. So that's port B, so that's B, that's C, that's A. So ABC give you 3 ports, and 24 I/O pins can be individually programmed, making it a very, very versatile chip. Actually, I would say, right? But it has been superseded by many nieces and nephews and grandsons. So 8255 has gone into the genetics and genes of many ICs today. But it used to be, it is still is one of the very versatile chips we had for defining ports. The 8250, we don't meet it that often nowadays, but in your 8085 kit, you might have it, 8250. So that chip is more often met as 16550, which is two 8250s in one chip, right? What it does is it takes something, I mean, grossly, if I just write it grossly, it takes something from the CPU, it performs a parallel to serial conversion, and then it moves out whatever you send from the CPU out through a link like this, right? And that parallel to serial conversion, uh, that that can be, oops, okay. So that can be either in this direction. So you have a serial data coming in and parallel data going to the CPU through an interrupt mechanism. It can also be in this direction, in which case you have parallel data coming from the CPU and serial data going out. Right? Now, when serial data comes in means it comes in on this arrow. I hope you're all able to see my arrows. There's a lot of clutter out there visually. But if the serial data comes in, right, it doesn't directly go through the chip. It goes into a register, right? Right? So the bits are captured into a register. That's the data register. Then once the register is full, this 8250 will actually interrupt the CPU saying, hey CPU, I seem to have got 1 byte of data from the outside world. Can you do something about it? So the CPU will then read this register into itself. And that we know is the general principle by which all IO pins work. So that's how it is. Um, why is this caption working downstairs? Oh, very nice. Let's keep that caption. I didn't know this existed in uh, PowerPoint. My speech is getting translated into a caption at the bottom. I think it's a very useful thing. I never knew this was there in PowerPoint, but it's fine. All right, so very exciting. Do you understand what I'm saying here? There is a 16550 universal asynchronous receiver transmitter. They perform the function of getting a parallel byte of data from the CPU and moving it out at a particular bit rate or baud rate, right, through a serial pin. So moving it out is the green arrow pointing from left to right. They also receive serial data at a particular rate. What is this at a particular rate? Who tells it that at a particular rate? Well, you tell the 8250 or 16550 what bit rate by programming that control register, whether it is 4200 bits per second, 9600 bits per second, 14400 bits per second, 119200 bits per second, whatever it is, you tell that 82550 that I want this many bits per second as the outgoing incoming rates. So you program it, you know it has a control register. In the data sheet, you will find that you can program this chip. But anyway, after it either gets a serial data or it sends a serial data, it helps the CPU write serial data to the outside world and get serial data from the outside world. Is this clear enough? I mean, without going into the details of how it does this, obviously
Yes.
it does it. It's so now do you think that by using our simple colored analogy that all IO devices in this world have data registers, status registers, control registers, you are now able to look at a diagram like this and say, oh, well, nothing to be afraid of. I can see the data registers, I can see the control registers, I can see the status registers. They must be the same, slight differences. I'll read the data sheet. That is exactly what this course is all about. Not about teaching you each of these blocks. that you will pick up by yourself. You are all natively intelligent chaps, right? So it's about telling you that, all right, this is just another IO device. This captioning is not working very well. So, okay. But it's very interesting, very useful. Okay. Serial interfaces. I skip this. Shall I skip it? You know now that a serial interface can be implemented, right? So if I even talk about it, I'll at the most say that, well, if you have these many bytes to send, right, then you need to precede it by 2 start bits and let's say 1 stop bit, 1 parity bit. So at the most I will say this. And who adds this start bit and stop bit? Well, the 16550 will add it for you. So all you have to bother about is how to get this register from this data 0 to 7, 8 bits from the CPU into the data register of the 16550. Once you push these 7 bits and you have programmed it to put these start bits and this stop bit, it will stick those 2 stop bits and start bits at the end of these 8 bits of data and send it forward. So that's like this. It's like cooking breakfast for your children. Like suppose I make a sandwich for my son. Of course, my son is now 26 years old, so I don't make sandwiches for him. But still, if I make a sandwich for my son, after making the sandwich, I just give it to, let's say, my wife and say, can you please wrap it in tracing paper or butter paper and put it in a tiffin carrier and send it to him. So my job ended with the sandwich making. The butter paper, the tiffin carrier, the booking of the Ola or Dunzo or Swiggy or whatever to transfer it to him, that is outsourced to my wife. Similarly, the CPU also outsources all serial inputs and outputs to the 16550. A very, very good thing to do because it does it so well, the 16550. So I don't have to explain this. Do I have to explain anything more in this? I should not, because we have some interesting things to do before we go. Right? I might take 5 or 10 minutes extra today because this is the last class I'm taking. And there is one significant part, DMA, which I need to talk about. Now, there are some common buses, right? So I chose to classify them as 0-wire buses, 1-wire buses, 2-wire buses, 3-wire buses, multi-wire buses, and buses I could not classify elsewhere. I call them other buses. Right? 0-wire buses means there is no copper wire between the CPU and the peripheral. So examples are wireless buses, Bluetooth, Wi-Fi, no wires, 0 wire. And IRDA is infrared buses. You must have met infrared buses in at least 2 situations in your local or in your lives. One is at the front of the printer. Right? Yeah, I don't know if I can show you that. IRDA port on a LaserJet. Okay, let me see if okay, there is actually a fast infrared port, but I don't see a image, so maybe I should look at images. Ah, yes, okay, good. So do you see this port on this LaserJet? Do you see this port, this little dark window? This little dark window is what is called an IRDA port. So if you have a mobile phone which has an infrared at the top, like some Samsung phones do have an infrared out there, you can point it at this port and say print this file. So you don't need a wire, you don't need anything, you can just print it. Right? It's very useful in a conference room. Right? So in a conference room, 30, 40 people come in, they have a meeting. You don't want to give each of them an USB cable and tell them to install a printer driver, etc., etc. Right? So you just say point your laptop. If your laptop has an IRDA port, point it at this and print. I mean, this was an option 10 years back. This was an option, but nowadays everybody prints over the network. So it's not an option anymore. So that's wireless printing with the IIDA series. Have you seen this ever? It's not very common nowadays. So I am a little apprehensive. Have you ever seen this in recent times? What is this? Oh, this is what I was doing yesterday. Right. So if you have not, just look at it. It's a very simple thing. The other example of an IRDA, not exactly an IRDA, but an infrared bus is the thing which goes on between your TV remote and your TV. Right. So there is a Philips uh, standard for the commands which are transferred from your remote of the TV to the TV. It's infrared, so that's also an infrared bus. So it's a zero wire bus. Then you can have one wire buses. One wire buses are not so commonly known, but if you go to Maxim or Dallas Semiconductors, you will find a lot of button devices. Button devices are all having one wire buses. The more common buses which you are exposed to are, of course, USB, but CAN, I2C, and SPI. Right? These are all two wire. 485, RS to 485 is another one. USB is the fourth one. So you can see all of these are two wire buses. Right? Then there are three wire buses. RS232, RS422, all three wire. And multi-wire buses. Multi-wire buses, some of them you are definitely exposed to. For instance, FireWire in Apple, in some higher end laptops of Intel 2, or SCSI interfaces. SCSI is small computer systems interface, I think, right? SCSI. So SCSI is old. We don't find, but SCSI used to be a very fast interface some time back. Nowadays, you don't find SCSI disks anymore. Right? They've all been replaced by what we call FiberNet and I think it's called Fiber Channel hard disks and SATA hard disks. Right? Then there is PCI Express. There is InfiniBand, Hippie, which is again a serial interface. Taxi, again a serial interface. And there are these other buses, right, like GPIB, right, which you will find at the back of your lab oscilloscope sometimes. If somebody has bought the oscilloscope with that option, you will find at the back of it there is a rather chunky looking port which is known as the IEEE 488.2 bus. Right? So that 488.2 bus is also called the general purpose instrument bus. So GPIB, it allows you to control your oscilloscope from your laptop. Right? Today, the GPIB bus is a master slave bus. So you can actually have one laptop control 16 devices in the lab. When you daisy chain from your laptop to the oscilloscope, from the oscilloscope to the printer, from the printer to the function generator, from the function generator to something else, you can actually daisy chain the device. So it's a daisy chainable bus, but it's not very common because it's a little expensive. Right? So nowadays we find what is called the LIN interface. So the LIN interface comes at the back of HP oscilloscopes nowadays. Right? So you can actually look at the LIN interface. Uh, it's one easy, simple way of connecting your laptop through the Ethernet port to an oscilloscope. And what can you do if you connect your laptop to your oscilloscope? Well, if you have anything on your screen, you can actually save that data to your oscilloscope. You can take a screenshot from your laptop. So if you're seeing something on the oscilloscope screen, or instead of turning knobs on the oscilloscope screen, you can turn those knobs using something like LabVIEW, right, from your oscilloscope. So there is a software called LabVIEW, LabVIEW, LabVIEW. So LabVIEW will turn oscilloscope time bases off, on, change the sensitivity, all from your laptop. What is the good thing? Is it just something which is nerdy? No, it's not nerdy. Sometimes we have, I'm not in our labs, which we do for undergraduates, but in the industry, sometimes you have to change a frequency in steps of, let's say, 10 hertz from 10 hertz to 40 kilohertz. Now, if you ask a man to do that, every 1 minute you change from 10 hertz to 20 hertz to 30 hertz to 40 hertz, it's going to take a long, long time to actually do it. Right? And for each of those input frequencies, you wish to, let's say, draw the output of your system and maybe take a Bode plot or do something like that. So what you can do is you can actually connect those devices, the function generator, the oscilloscope, the spectrum analyzer, connect it to your laptop. From the laptop, send a command to the frequency generator, give a output frequency of 10 hertz. Then you tell the spectrum analyzer, what are you measuring? Input it to me. So the laptop will both set the input and take the output. And then in the next microsecond, it will make the input 20 hertz and measure the output. Then it will change it to 30 hertz and measure the output. So we can actually do a measurement run in, let's say, 2 hours. What would have taken us 3 weeks will be done in 2 hours. So that is why we use these bosses. Okay, so we are more or less done with this part of it. So I'll just move on to the next part of it, which is DMA. Okay. Now you have done memories, haven't you? You must have covered memories in some other class, right?
Memory
Have you covered?
covered in this course. I have already covered the memory except the cache memory, which I will,
Oh, you have covered cache memories. Okay. In that case, let me briefly give you two memories. Okay. Let me give you this. So that's a very simple slide for a memory. A memory is a place where we store ones and zeros in a computer. So you have a CPU which has a 1 to store. You have a yellow memory which has space in which you can store this one. Right? That one, the way it looks in that purple register there, it's as if there is a single bit one, but it can be a byte called 00000001. It can be that byte. I mean, I'm lazy, I didn't write that, but that's what happens. So this is you can store it using latches. You know that there are latches, and latches are bistable devices. They have two states, and there are so many latches. Set reset latches, Jack Kilby latches or JK latches, toggle latches, T latches or T flip flops, delay latches or delay D flip flops. So set reset, Jack Kilby, T, D, right? These are all flip flops. But ultimately, what these flip flops do is that we have a CPU and we are writing it to a 1-bit memory, let's say. So what do you need to write it to 1-bit memory? You need a 1-bit storage space, so you need one flip flop in the memory. You need an address for that flip flop. And when you read that flip flop, 1 bit will come out over this data bus and go back into the CPU. Not very useful, but as a starting point, not very bad or not very wrong either. Right? Now, obviously, you don't want to store 1 bit. Right? Then you need to store more than 1 bit. So let's have another bit. So what does the second bit need? It needs another address. So you have 000 for the first bit. You have 001 for the second bit. So that's 2-bit memory. Again, not very useful. But what is the width of the data bus? The data bus is still 1 bit wide because at any one point of time, you're either reading the first location of the memory, which is 1 bit, or reading the second location of memory, which is 1 bit. I use the word reading, right? But you can also write to the first location in memory, address 0000, or you can write to the second one. But it's all still a 1-bit transaction, right? But 1 bit is not very useful. So we have to store a little bit more, like maybe a byte, at least a byte, right? So if you store a byte, so I can start putting more than 1 bit in the same location. So I have 1 and 0. So this is a 2-bit, right? So 2 bits are better than 1, not still very useful. But what it does is if you put 2 bits in the same location, then your data bus has to be 2 bits wide. To read this 1 and 0 over this data bus, you need a 2-bit data bus. The address bus doesn't change because we are still addressing the whole of this one location. So if you stretch this a little further, you'll find that you can put, let's say, 4 bits, maybe 8 bits, maybe 16 bits, maybe 32 bits in the same location. So address 0 refers to 32 bits of storage in the same location. So whenever I say read what is there at address 0 and there are 4 bits at address 0, I need a 4-bit bus to take this. And now if you look at this in the previous slide, my bus was one way. It seems I was only reading. But now I have cleverly drawn this bus both ways because I can both read and write. And because I did that, I added a wire here. So you can see at the bottom of this slide, if I, oh, why has it become so big? For some reason, my slide has become very big. Anyway, you can see it here. I've added a control read write out here. And so I've made my data bus cleverly bi-directional. And if you don't like these colorful, trivial looking diagrams, you can take the diagram of this from Hampshire. And you didn't probably notice another clever thing I did in the previous slide. That is, apart from this location, which is very much like this slide, I added 4 bits here, 1001, which is a sense amplifier plus register. So if I was actually looking at address 0, then 1001 would go into these 4 bits. These 4 bits are common to whatever I read or write. So 1001 would move here and these 4 bits would be read over the data bus. So there is this sense amplifier which is a part of every memory, right? It's a register cum sense amplifier. So you have a sort of electrical sensor and a electrical, not sensor, but sensor, to sense what is there inside this bit and put it in this register. So it's something to sense. Right? So that's what Professor Hampshire writes here. So he says there are these bits in the memory, but you have a sense and a read. Sense is like a read. Write is like, of course, writing. So this is bidirectional. So it's data input or output. So this set of sense read in the south of this diagram is what I have drawn in the north of my diagram. These 4 bits. So far, no problems, I hope.
Yeah, these things I have discussed.
Correct. So now once there is in this thing, there is only one slide I need to actually look at. That when you have this array, these bytes in the memory, you can actually organize them as rows and columns. Right? If you organize them as rows and columns, then what happens is something very nice, because when you have a row and a column and you have sense amplifiers, memory can be split into banks. So that gives rise to this whole process of dynamic RAMs and the refreshers which you have in dynamic RAMs. So this part, if you have covered, then you will know that memory therefore can go, something can go from memory to an IO device, from an IO device to a memory, and from memory to memory, right? But the way in which it goes is that somebody in the CPU actually says read. So this part of the memory in this bank of the memory moves into the sense amplifier. This sense amplifier is taken into the CPU. So if I draw this out, it is somehow my slides have become a little bigger than what I thought they would be. I don't know why that has happened, but it is this sense amplifier. I've done something maybe. Okay, I can only see it in this mode. Fine. All right. So this sense amplifier is read into the CPU, and then it is rewritten to another part of the memory. So if you want to shift something from the memory to the memory, you have to involve some temporary register. And memories don't have a temporary register. So that temporary register has to be borrowed from something inside the CPU. So read from the memory, turn the cycle of memory access into write, and write into memory. Right? There is only one problem here. The problem is This is a very expensive thing. If I had to explain what is expensive about it, if you look at this whole scheme, you have memory which is organized into banks. This is bank 1, bank 2, bank 3, bank 4. And I am reading this byte. This is the byte I am reading. So what is happening is this byte is actually moving into the sense amplifier of that bank. Right? Now, while it is doing that, the memory, being a DRAM, is actually refreshing this. So it is refreshing this bank, it is refreshing this bank, it is refreshing this bank. Now, having read these sense amplifiers, it is going to now then read this into CPU and then write it back to another bank. So this read and write, the number of cycles you need is a little uh, expensive in terms of, let me see if I have those cycles somewhere. Okay, I have this. So read to write switch takes 2 cycles. Write to read cycle switch takes 4 cycles. So if you want to read from this memory and write to the memory, you need 2 plus 4 cycles. Now that's expensive. For every byte you read and write back to the memory, you need 6 cycles minimum. And between the 2 switches, you need to put some knobs, no operations. So it's 6 cycles plus. And depending on where you are accessing, where you are writing, the switch frequency will change. Now that is not something you want to do. You don't want to have this inefficiency of the switch cycle in the memory access. Just one slide before I go out into the DMA, which I'm supposed to do, is that all memory controllers have a memory specific part called the front end and a memory non-specific part called the back end. So you have a front end and a back end, and both of these are part of the memory controller. So I actually would say there is a memory and there's a front end and there's a back end here, and the CPU writes here. The necessary commands for the memory are generated by this controller. Memory data is read and fed back into the CPU. So these are the functional blocks. But this is a very expensive way of accessing the memory, especially when you have a lot of data to be read from the memory and sent to an IO device, or a lot of data to be read from an IO device and sent to the memory. Example, suppose I have a camera and the camera wishes to store a frame, or let's say 25 frames per second, into my memory. Each image from the camera is so many megapixels long. If I involve the CPU for every register of data I read from the camera and store into memory, it's going to take a hell of a time to just store one image frame. So we need some other way. That some other way we need is the justification for what I'm going to say next. What I'm going to say next is that we actually need something called direct memory access, right? Because memory access is so expensive otherwise, time-wise. Not expensive in terms of cost, economic cost. Right? Okay, I don't have a slide. Okay, maybe I meant to put something. What is DMA? First of all, direct memory access means sending data from memory to IO. That's one type of direct memory access without involving the CPU. Second is sending from IO to memory without involving the CPU. Sending from memory to memory without involving the CPU. There are 3 forms of direct memory access, right? So if you look at what Professor Sarangi says, so the DMA controller, in my slide, I forgot this part, the unit that controls all these transfers is called a DMA controller. And it is another IO controller. You program it and then you let it work on transferring data from the memory to the memory, memory to IO, IO to memory. So it's just another IO device, right? Which does memory to IO, IO to memory, memory to memory transfers. And you know how IO devices work. But let's see what Professor Sarangi says about this. He says in this slide that if you transfer data byte by byte, the processor is tied up. Now, even if you use memory mapped IO, it requires a large amount of CPU time. So what you do is you outsource these transfers to a memory controller or a DMA controller. So assign the work of transferring data from main memory and IO devices to the DMA engine. Right? What is the word engine? Well, engine is a term which we use for something which drives something. A car engine drives the car. So a DMA engine drives the DMA. So I can say a memory controller engine, a data sorting engine, a Fibonacci sequence generator engine. Right? It doesn't mean engine in that sense. It means it's a thing which turns out. It's a finite state machine which turns out things. So we will often find this word, network engine. Right? Engine means something which handles DMA. Now the DMA is part of the North Bridge chip. Oh, now we hear this word North Bridge coming in. But now we know what a North Bridge is because we talked about it in split buses. We said there's a North Bridge and a South Bridge. And memory to memory, memory to IO, IO to memory are very, very fast transfers. Right? So if you remember the analogy I said about the director's path into the main building and the cafeteria's path into the main building, obviously the DMA qualifies to be in the director's path because it's a very fast transferring device. So it's part of the North Bridge chip, not the South Bridge chip. South Bridge chip, slow transfers. North Bridge chip, fast transfers, premium transfers. So it has access to main memory and to IO devices and it can transfer data between them. So how does one outsource this transfer? So you tell this controller that I want 25 megapixel mega registers of data. Let's say 25 megabytes of data from location so and so in memory to be transferred to this IO device, and then you tell me when you're finished. So the DMA will load the value 25 mega registers into a control register. It will tell the CPU, I'm going to transfer data. So can you please give me the bus? Because data needs the bus. I and that IO device are now going to talk for the amount of time it takes for me to transfer 25 mega registers into that device. So please let me have the data bus and the address bus for that amount of time. I will put the address, I will increment or decrement the address as you have programmed me, and I will make sure the data is received by the device. You don't have to come into the picture. Fine. I hope I have a story for this, but do you get this explanation? That there is a chip somewhere on this computer architecture board, as part of this computer architecture, which takes over the task of transferring bytes from memory to IO. All it needs is from where should I transfer, how many bytes should I transfer, and at the end of it, it will raise a request, an interrupt request saying transferred. Now what? I'm relinquishing the bus. Do whatever you want. So most of the time, the DMA controller will just spend in its idle state. Nothing to do, fine. But every once in a while, the CPU will tell it, hey, go to CPU, go to memory location 0800 and transfer the next 16 bytes to that printer. Then the DMA will say, okay, I got it, 0800, next 16 bytes, please give me the bus and keep quiet, do whatever you want. When I'm done with these 16 bytes of transfer, I'll interrupt you. That's simple to understand, isn't it? So the processor programs the DMA controller with the addresses, the size of the data, and the IO address location. Right? Where to take it from, how many data bytes to take, and where to send it to. This is all that you will have to send to the DMA controller. And once you do that, right, you can actually transfer this in burst mode. So lock the front side bus and the IO devices till the entire transaction is over. That is, you hog the bus. Right? Or you can cycle steal. Cycle steal means when Professor Rajakumar is coming down the staircase, the cafeteria fellow is waiting inside his cafeteria with his sack of samosas saying, director is going home, let me wait for 5 minutes. When the director's car leaves, he rushes down and tells his truck, okay, let's load the samosas. You go to the back of the building. I'll call you again for the tea. Now the director comes back after lunch. The cafeteria fellow is again hiding. So that's called cycle stealing. So you use the bus in stolen cycles. When the director is not going up and down the staircase, you can use it for tea and samosas. So that's another way of doing it. I mean, that's more intelligent, but it transfers the data in smaller chunks, right? And you have a lower priority. If the director is on the staircase, you don't go onto the staircase and say, Professor Rajakumar, please wait, I'm carrying 3 buckets of tea downstairs. You don't do that. You wait inside the cafeteria. When his car leaves or he's inside his office, you then use the staircase. That is also simple to understand. You can do that, or you can do split transactions. That is, my transactions are only on the North Bridge bus or the North bus. So you do whatever you want in the South bus, or I am doing only in the South bus. You do whatever you want in the North bus. So that also is a possibility. So, so what we can classify this is that we have 1 byte, 1 word transfer, or block transfers. Many bytes, many words, many bytes, right? So this is going to be slow if we involve the CPU. So the CPU says, so the DMA controller says, if the CPU can do it, else you get out of the way. Right? So that's what the DMA says, get out of the way. Get out of the way means tri-state your data bus and address bus from inside. That is, down your shutters, lock your houses. I am taking over the roads. Right? Today is my day. So that's what the DMA control says when it says get out of the way. Now, I have a story time for this. The story time is let me add something here. Just occurred to me, school bus downloads into the third example. I hope you have seen these showdown scenes in Western films. That last scene where the villain and his friends are coming down the street from one side, and the hero, usually alone, is walking down the street from this side. Have you seen a Western movie like this? I took this scene from High Noon, which is a 1952 movie. That's why it's black and white. But you must have seen Western movies like this, or do you not see Western movies nowadays? Good, bad, and ugly. Come on, some yes, no. The showdown
No.
scenes are not only in Western movies; they are in Hindi movies also. That last scene, with the mother tied up and hero arriving, villain laughing. That showdown
Yes.
scene, What has happened to the shopkeepers in this photograph? What have they done? They
Shut
have
down.
downed their shutters. They are in high impedance mode. They are not talking. They are actually not interfering with whatever is happening on the street. Right? All the houses have people stuffed into them, right? Who are doing their own thing. Somebody is cooking, and if you ask anybody there what is happening on the street, they say, I don't know. The shutter is locked. The door is locked. I'm just cooking breakfast. So the CPU is doing its own thing inside this house, inside this house, inside this house. And what is happening on the street is there is a one-way transfer. The hero is walking from the police station towards this point. At this point, he will shoot the villain, and then the movie will end. Right? So the DMA is owning the bus, just like this hero and that villain are owning the bus. What is getting transferred in this photograph? The bullet. The bullet will get transferred from the hero's gun, right? Or if the villain shoots a bullet back, right, then the hero will catch it in his hand if he happens to be our famous, what's his name?
Rajnikant.
Rajnikant. He's Rajnikant. He'll catch the bullet and throw it to one side. Right? All these transactions are high-speed transactions. Bullet from there, from bullet to there. So then at the end of it, somebody will die. Usually the villain, sometimes the hero, and then the movie will end. So that's the showdown scene. That's very much like a DMA transfer. The other DMA transfer is this bull run, which has been made famous by uh, our Hrithik Roshan's movie. Right? What is that movie? Dil
जिंदगी
Dil.
ना मिलेगी दोबारा.
Yes. ZNMH. No, मिलेगी दोबारा. ZNMD. Zindagi na milegi dobara. Made famous. Of course, it has been happening for centuries. Right? This Pamplona Bull Run. What happens in the Pamplona Bull Run? There is a set of bulls, right, which are coordinated from some corral. They are in a corral, and somebody knows in that town, Pamplona, that these bulls must be released at 9 o'clock, right? If you remember the movie, Hrithik Roshan and his friends got up early in the morning to go there because they knew that it's a timed time transfer. The bulls will not wait for them. Right? It's not that the bulls will sit around at their corral picking their teeth and saying, Hrithik Roshan has not come, let's just hang around for 5 minutes. They won't do that. At 9 o'clock, the bulls will be released, and in a mad rush, let's say 32 bulls, just to choose the analogy with 32 data bits, will rush along the street, and the destination is known. They will all go through the same destination to the last point where they will be shut up, and shut up means closed into a room and given breakfast. So bulls are served breakfast at the end of this run. So that's the Pamplona bull run. But you can see that all these guys at the sides are in a high impedance mode. There is a barrier between them and the bull, right? And anybody who is in the bull's path has to get out of the path, like this fellow out here, right? So this means relinquishing the bus. Right? So you relinquish the bull run bus so that the bulls have a free transfer. And you can recognize that this is a far faster way of transferring 32 bulls from one place to another place, right? Saying 32 bulls will go at 9 o'clock. In the next 5 minutes, they will rush along these roads and go into a place where we will serve them breakfast. That's the service. So the Pamplona Bull Run is a good example of a DMA because the DMA controller will say at 9 o'clock, I'll start a memory transfer from this location to this location, get out of my way, whichever way you have to establish a high impedance state on your bus, close your shutters, climb the windows, put a barrier, whatever you do, don't get into my bus. I need a free bus. I just added this third example. It occurred to me while I was talking. Suppose the principal of a school owns 20 buses and children arrive in those buses. Right? And usually schools will have a bus coordinator ma'am. So bus coordinator ma'am says, which bus is this? This is bus number 9. All right, this came from where? Arugul. Okay, Arugul bus number 9. Can you please send all these children to room number 24? So please take the second door so that principal ma'am is not disturbed. So the bus conductor makes sure all the children get down, form a line, walk in line to room number so and so, right? And the principal just watches from her window that, okay, the bus coordinator has downloaded all the children in bus number 16 and they are all going into room number 32. Now that's an example of a DMA, right? Now suppose when the children get down from the bus, suppose 5 children want to get back into the bus. They say we have forgotten our water bottle, right? Now, what will that conductor do? Now, all the children are getting down, but 5 children want to go back in. So, what he'll say is, come to the side and form a queue. That's exactly what the bus conductor does. Form a queue, which means use a temporary swap space in which you keep those 5 children. Because making children come down from the bus is like a read operation from a memory device. Making children go into the bus is like a write operation into a memory device. To switch from a read to a write takes time. So if you say, okay, everybody who's getting down, please stop while I go in and get my water bottle, then it's going to take more time. So what he wants to do by forming a separate queue for these 5 children who want to go back into the bus is to incur only one read to write swap time payment. So after those 71 children have got down from the bus and have started moving into the classroom and are out of sight, these 5 children are said, go into the bus and do whatever you want, your water bottle, tiffin, handkerchief, retrieve it and come out. So this arbitration is taken care of by somebody, the conductor. So these are all pehlus or aspects of direct memory access. Now, fortunately for us, there is a chip which handles this for us, 8237. And it is a very familiar looking chip. because you see, I told you in the beginning, whether you believe me or not, that once I told you about the data, status, and control registers, every device in the world will look the same. And now, when you look at it, your eyes are trained. You are not going to be daunted by, oh, what are these pink things? What are these purple things? You'll say, where is the data? Where is the status? Where is the control? I see all of three of them. There is nothing which is unfamiliar to me, right? So if I then look at this 8237, I hope I can locate that 8237 data sheet 8. No. I think I made a mistake. 8259. I made a mistake. Sorry. Okay. So 8237A from Intel. The same diagram I showed you. But what you will see here is, look at this. So you have 4 DMA channels, independent or auto initialization of all channels, memory to memory transfers, memory initialization, address increments or decrements, which effectively says that the 8237, when it is counting down 16 bytes to be transferred, is basically a finite state machine counting down like a register. It says address 1 transferred, next address increment by 1 transfer, next address increment by 1. So it's going to do that. So it's address increment or decrement. It can be cascaded, right? And it will also interrupt the CPU. If I go down into the data sheet of this, it's a long data sheet, but we don't have to read all of it. We just have to think that if I glance through this data sheet, just like when I glance through the Times of India, the Times of India doesn't scare me. So now I will not be scared by this. So I said, most of the time the 8237 will be twiddling its thumbs waiting in idle state. So do you see this idle cycle? When no channel is requesting service, the 8237 will enter the idle state and perform system idle SI states. Right? It will just keep sampling, checking, picking its teeth, etc. Fine. Then it will work in 2 cycles, idle cycles and active cycles. Idle means doing nothing. Active means doing everything else it is supposed to do. And active cycles have 7 states. The 8th state is the idle cycle, right? That's inactive. Now let's go forward. In the active cycle, you can have single byte transfers, you can have block transfers, you can have demand mode transfers, and you can have cascade mode in which more than one 8237 is connected to an 8237. And the 8237 only talks to the microprocessor through 2 bits, 2 wires, hold request and hold acknowledge. Once you say hold request, right, the CPU will say hold acknowledge. So once you tell the 8237 start a DMA, it will say, all right, I am ready through the HRQ. And once the hold acknowledge comes, it knows the CPU has stepped out of the picture. I can now transfer data from some memory to IO, IO to memory, IO to, not IO to IO, but memory to memory. But let's just see. Did I tell you the right thing when I said these transfers take different amounts of time? So if I look at it memory to memory, then priority transfers. But I just want to say, am I vindicated when I say that they take different amounts of time? Let me see if I can find that in the data sheet. Somewhere Intel should tell me, yes, memory to memory is very slow, but memory to IO can be fast. So I just want to see if that is necessary. Okay, here is a familiar word. The temporary register is used to hold data during memory to memory transfers. So when you transfer from memory to memory, you need to temporarily hold the data. So the temporary register is inside the controller, not inside the CPU. Right? Now, I am searching for something which Intel will say, yes, Prof Kar, you did not lie to the students of IIT Bhubaneswar. I'm quickly searching whether I can find anything in the data sheet which tells me how how long it takes from memory to memory. Well, Murphy's law will work. I will not probably find it, but if I can, maybe I can, maybe I can't. Let me quickly scan through this.
So how long will be today's class?
We are done, finished. it was only to search for a table saying memory to memory is slower. I didn't find it, but if you search slowly, you'll find it. You'll find that memory to memory transfer is almost 5 times slower than memory to IO and IO to memory. I am done. Time for questions. And this is also my last class with you. So any questions will be the last set of questions I answer. And you might be in a hurry for another class, so I completely understand if you don't ask any questions. Professor Dogra, that might be right. They may have another class. I'll just stop sharing my screen. And I would very much like it if you would send me back some feedback on how you found these classes. Were they useful? What did you learn? What did you feel about the classes? If you just send me email, I would be more than happy. Right? And you can find my website. My email is subrat@iitd.academic.in. So subrat@ee.iitd.ac.in. So please email me. So Dogra, I'm done. I think Professor Dogra is.
Yeah. Thank you, Professor Kar.
Thank you. Thank you.
Thank you.
Bye bye, everybody.
Bye.
Thank you, sir.
Thank you, sir. सर
Yes.
सर आपकी स्लाइड्स कहाँ से मिलेंगी?
किताब में हमेशा and SR
नहीं,
Sarand.
I mean मतलब PPT वाली.
मैंने तो वहीं से टिपा है इसको. I've copied everything from those books. That would not be right that I pass them as my slides. You have my recordings, but everything in the slide is from those two books. So I suggest you buy those two books only. They are recommended for you. Everything is from those two, except of course my stories. My stories are not in that. So that you will find in my recording. You see, when I take stuff from somebody's book, I can't pass it off as my slide. Right? So that's copyright infringement. Every time I take something from somebody's book, I say I took it from Hamisher, I took it from this data sheet. I'm just looking at Professor Sarangi's page number, so and so. So it is their copyright. Right? They chose to give me that information for academic purposes. So I'm not going to give you any slides, but please look at my recordings. And you can always pause my recording and say, that's my slide. Okay?
Okay. Okay.
Any other questions, responses? Does anybody have anything to say? If not a question to ask.
एग्जाम में कैसे क्वेश्चन?
एग्जाम में क्या पूछो?
मस्त लगेगा.
एग्जाम में
प्रॉब्लम्स.
Exam questions. What will
This
be the same
type, like, like, can you say 1-2 samples?
Yeah, of course. Suppose I have a DRAM and I give you that it is organized as rows and columns, what do you think would be the minimum number of address cycles between the row axis and the column axis? That's a sample question. ये भी recording हो रहा है तो मैं in one sense I'm leaking the question.
ये एग्जाम में आएगा सर?
आ सकता है. तो आप क्या करेंगे? आप you will look at this slide, right? Do I have that slide on screen? Maybe I do. तो कहाँ है वो slide? कहीं है क्या वो slide? शायद इन स्लाइड्स में है नहीं वो. That मेरा जो वेव ड्रम वाला स्लाइड था ना उसमें तो डेफिनेटली था. So if you look at yes, look at this slide. RAS है, यहाँ CAS है. तो मैं पूछ रहा हूँ आपसे कि how many booms between RAS and CAS? So the idea is that okay, if you have a knob, then you have one boom. If you don't have this knob, you don't need anything. They will be on subsequent booms, isn't it? तो जवाब तो यहाँ से मिलेगा, but समझ आपको कहाँ से आएगी? समझ आएगी आपको कि RAS के बाद CAS आता है और RAS के फौरन बाद CAS आता है. So between RAS and CAS, there need not be any clock cycles unless the memory is a slow memory. So if you use a fast enough memory, this knob will vanish and there will be adjacent clock cycles between RAS and CAS. So row, which is an address, column, which is an address, RAS, which is a strobe, column address strobe, which is another strobe. So आपको तो I have drawn this diagram here when I said that I have a address and a strobe. So address and a strobe. तो वही चीज I'm telling you in this other diagram that you can have a address and a strobe. So अगर if you have understood it, then you will say, well, the RAS will come immediately on the same boom as the row address. The CAS will come on the same boom as the column address, and they can be adjacent. So the number of clock cycles is actually 0. Right? Is that the right answer then? Does it answer your question?
Yes, sir. Sir, for preparation purpose, Carl Hamacher and one SR Sarangi book we should refer.
Yes, I would prefer you pronounce Professor Sarangi as Sarangi, not Sarangi. Sarangi तो वो म्यूजिकल इंस्ट्रूमेंट होता है. सारंगी नहीं तो सड़ंगी है. स्मृति रंजन सड़ंगी, like a SADANGI, Sadangi. Professor Sadangi's book that is prescribed for you, Hamacher's book, which is also prescribed for you. वैसे सवाल तो प्रोफेसर डोगरा बनाएंगे. आई एम नॉट द पर्सन हु सेटिंग योर क्वेश्चन पेपर, बट मैं कह रहा हूँ अगर मैं सेट कर रहा होता तो मैं ऐसे सवाल करता हूँ which actually test your understanding rather than how much I would actually give you a waveform like this and ask you the question. देखो आप में से जो भी देखेगा इस वेवफॉर्म को ना, देखो से हाँ RAS और CAS के बीच में एक नॉब है and so therefore one clock cycle for RAS, फिर एक knob cycle, then one CAS, so the answer is 1. पर वो गलत होगा because unless you have understood the principles of address and strobe, that knob is not necessary. तो अगर concept test करना है, I would ask this question and say यही diagram है, You don't have to depend on memory. इसमें से पढ़ के बताओ RAS and CAS के बीच में minimum number of clock cycles कितने होने चाहिए? तो 1 गलत होगा, 0 सही होगा. Understood? ये सब रिकॉर्ड हो रहा है, तो कहीं कोई ये न कह दे कि लीक कर दिया उन्होंने क्वेश्चन पेपर. मैं सिर्फ बोल रहा हूँ कि क्वेश्चंस कैसे आएंगे, किस तरह के क्वेश्चंस. और यहाँ पे तो कोई अग्रवाल्स गाइड होता नहीं है, अरिहंत गाइड टू कंप्यूटर आर्किटेक्चर. तो सवाल ऐसे ही होते हैं, right? फिर भी सिंपल होते हैं, क्योंकि जिंदगी में जो सवाल आते हैं ना उभर के, वो इससे भी कठिन होते हैं.
Yes, right.
So anything we ask is going to be a sanitized, diluted version of what you will meet in real life.
This is absolutely right.
We are done. We are done. And if you don't have any comments, I'll just stop and say goodbye.
So on behalf of the entire class, sir, thank you for your so much of time you spent with us, and it was really nice experience for me also to learn so many things during
Okay,
this
good.
process. I believe students must have enjoyed all of your lectures.
I don't know. Students enjoy grades, but they don't enjoy grades nowadays. हर्ष ताली बजा रहे हैं, सुशांत ताली बजा रहे हैं, पूरे क्लास को सुशांत बना दिया.
Right.
But anyway, thank you all.
Yeah.
Bye bye.
Thank you, sir. Bye bye.
But do send me an email,
Thank you, sir.
the students.
Yes.
Bye bye.
Bye, sir.